Why do some of the most critical trains in the world look nothing like passenger locomotives or freight engines? And how do these unusual machines quietly prevent disasters, move rockets to space, and even shape global security? Stay with us and subscribe as we continue investigating the hidden infrastructure systems that keep modern civilization functioning. This story begins not with spectacle, but with precision under pressure. On a humid morning in Augusta, Georgia, a Norfolk Southern locomotive glides along the main line. But this is no ordinary train. Beneath its frame, a pod bristling with sensors is mapping every inch of rail at highway speed. This is the Automated Track Geometry Measurement System, ATGMS, a rolling laboratory designed to reveal microscopic flaws before they become disasters. Inside the operations cab, the atmosphere is focused. Lasers sweep the railhead, resolving surface deviations as small as half a millimeter. Ultrasonic transducers pulse high-frequency sound waves deep into the steel, searching for cracks invisible to the naked eye. Every jolt and vibration is captured by accelerometers and inertial units, while a global navigation satellite system receiver pins each measurement to a precise location, accurate to the centimeter. During a single inspection run, the system compresses and transmits up to 3 terabytes of data, each byte a potential warning. In 2016, the crew flagged a subtle irregularity near milepost 37.5, a 4mm head check detected only by the ultrasonic echo pattern. The data analyst's voice cuts through the radio. Defect confirmed, priority 1. The engineer reduces speed to 30 miles per hour, and within minutes, a slow order alert is issued to all following traffic. The numbers are stark. Historical models showed a nearly 1% chance that this defect could escalate to a catastrophic break within 30 days. Maintenance crews receive the coordinates, and a grinding team is dispatched before nightfall, erasing the threat before it can grow. Across the network, these mobile labs find 3 times as many microcracks as traditional inspections. Each detection is a small victory against derailment, a data-driven intervention that keeps commerce and communities safe. The ATGMS does not just measure steel, it quantifies risk, transforming invisible fatigue into actionable intelligence. For the crew, the stakes are never abstract. As the operations lead says, we are looking at a rail defect before it is even a crack. That is proactive safety at terabyte scale. As dusk settles over Atlanta's rail corridor, a different kind of train takes over the main line. The Lorem RG400 grinder, bristling with a 24-stone array, advances methodically, up also. Each stone powered by a 30-horsepower motor. Sparks spray across the ballast as the machine shaves away up to 1.5 millimeters of hardened steel per minute, restoring the rail profile that heavy freight and relentless traffic have warped out of shape. This is no spectacle for its own sake. Every pass is calculated, every gram of steel removed with economic intent. Grinding costs about $45 to $55 per ton of rail removed, a fraction of the $150 to $200 per ton it would take to replace worn track outright. On the Atlanta corridor, these overnight operations save between $4 and $6 million each year, extending rail life by 15 to 20% and cutting down on costly replacements. The grinder's closed-loop water system pumps hundreds of liters per minute, cooling the stones and suppressing dust, while a foam-based fire suppression system stands ready to douse any stray embers. Sensors monitor temperature and stone wear in real time, feeding adjustments to keep the process within safety margins. At the heart of this operation is the foreman, a veteran with years of tactile experience. He checks the grind by ear and by feel, trusting both the data and the subtle vibration under his boots. If it isn't smooth, the whole freight network suffers, he says, eyes scanning the dashboard and the rail ahead. Each pass is a balance. Remove enough material to erase fatigue and corrugation, but not so much that the rail's lifespan is cut short. The grinder's profile lasers verify the work as it happens, closing the loop between inspection and intervention. What looks like brute force is, in reality, a precise, preventative remedy, one that turns raw horsepower and abrasive grit into millions in savings and decades of reliable service. At Baikonur Cosmodrome, the journey of a fully assembled Soyuz rocket begins not on a launch pad, but on rails stretching across the Kazakh steppe. The transport carriage itself is a feat of hidden engineering. 6 massive bogies, each fitted with hydraulic springs rated at 1.2 million newton-seconds per meter, absorb every jolt and ripple in the track. The rocket, weighing 300 tons, rides on a platform designed to spread its load evenly across dozens of axles, keeping the stress on each wheel set well below the limits of standard heavy-haul rail. The desert climate throws its own challenges. Temperature swings from -30 to +40 degrees Celsius can cause the rails to expand or contract by more than a centimeter per kilometer. To compensate, the carriage uses expansion joints and real-time track temperature monitoring, while sandstorms are kept at bay with filtered air intakes and protective shrouds. Every meter of travel is tracked by a laser-based alignment system, feeding sub-millimeter data to the control cabin. The logistics officer overseeing the move describes it simply: rail is the quiet, steady heart that delivers a rocket to the sky without shaking its dreams. Vibration damping is not left to chance. Elastomeric pads and dynamic brakes work together to keep accelerations below half a G, even when the train crosses minor track irregularities. Stopping a fully loaded rocket train from 40 kilometers per hour takes about 400 meters. Dynamic electric brakes regenerate energy into onboard batteries, while pneumatic discs provide a redundant failsafe. In this environment, every detail is measured, every risk anticipated. The result is a rolling laboratory in service of human spaceflight, where the strange shape of the train is dictated not by spectacle, but by the unyielding demands of physics and precision. The same principles, distributed load, vibration isolation, relentless alignment, will soon be pressed into darker service as the story of rail's double life unfolds. In the closing years of the Cold War, the Soviet RT-23 Molodets missile train became a rolling paradox. An ordinary-looking freight consist hiding the most powerful weapons on Earth. Each RT-23 train carried 3 intercontinental ballistic missiles, their launch cars indistinguishable from refrigerated boxcars. Yet inside, hydraulic leveling systems could stabilize a 100-ton missile to within plus or minus 0.1 radians, even on uneven Siberian track. The entire platform was engineered for deception. Manifest paperwork listed agricultural goods, while camouflage paint and civilian routing masked military intent. Crews could operate autonomously for up to 30 days, living in cramped quarters as the train vanished into a network stretching over 100,000 kilometers. By 2005, the last Molodets train was decommissioned, but its legacy haunts arms control to this day. The United States once pursued its own rail-mobile missile project, the MGM-1, but canceled it in 1963 after engineers struggled to achieve the same launch stability without massive track upgrades. In the end, the U.S. favored roadmobile launchers, leaving the rail concept to history, at least until new actors revived the idea. On September 15, 2021, North Korea launched a KN-23 ballistic missile from a flat car at 2:14 a.m. local time. The train, painted to blend with standard freight, carried a civilian manifest listing construction steel. Commercial satellite analysts working with open-source intelligence pieced together the event by comparing images before and after the launch, catching a 3-meter-high container that had not been there the previous day. The timing exploited a gap in satellite coverage, taking advantage of the 12-hour revisit window that leaves large sections of track unobserved. According to a Russian Academy of Sciences study, rail mobility can reduce detection risk by up to 68% compared to fixed launchers. A Cold War historian describes it as the ultimate game of hide-and-seek on steel rails. For modern analysts, the dilemma is stark. Rail offers unmatched mobility and concealment, but at the cost of verification. Missile trains turn civilian infrastructure into a strategic wildcard, challenging treaty monitoring and blurring the line between commerce and deterrence. In the world of strange trains, what looks like a logistical oddity is, in fact, a calculated response to the pressures of geopolitics and surveillance. In 1971, Tampa International Airport faced a choice that would shape how people move through airports worldwide. Planners wanted a system that could shuttle passengers quietly, reliably, and without fuss between terminals. Designers debated futuristic options, including magnetic levitation, linear induction motors, and even cable-pulled trams. But the final answer was something less flashy and far more practical: a rubber-tired automated guideway transit called AGT, powered by a 750-volt direct current third rail. Each car measured 12 meters long and could carry up to 70 passengers, gliding along a 2-kilometer dual-track loop. Instead of steel wheels, the vehicles ran on rubber tires for better grip and smoother stops on the airport's steep grades. Underneath, a spring-loaded copper shoe drew power from the third rail, feeding 4 motors of 150 kilowatts each per car. Control was handled by an early programmable logic controller, which monitored speed, doors, and emergency brakes, ensuring the system could stop safely if anything went wrong. A former Westinghouse engineer later described the decision. He said they could have chased the latest technology, but the airport needed something that would work every day without surprises. The result was a rolling test bed, an automated, low-maintenance train that quietly proved its worth, setting the standard for airport people movers around the world. In July 1973, a rail test vehicle in Pueblo, Colorado, reached 183.68 miles per hour, faster than most passenger trains ever built. The secret was not just brute force, it was a hybrid propulsion stack that combined a 15 kilonewton turbojet with a linear induction motor, both controlled in real time by a closed-loop system. The engineer in charge described the challenge as synchronizing 2 different beasts: the jet delivering raw thrust, the LIM providing precise traction. To keep the coils from burning up, a liquid nitrogen spray cooled the LIM windings, capping temperatures at 200 degrees Celsius, even as electrical loads pushed toward 800. Tuned mass dampers quashed vibrations above 30 Hz, while a UHF telemetry link streamed 16 channels of live data to a ground station. The safety net included redundant kill switches, magnetic eddy current brakes, and a mechanical clamp that could stop the vehicle if anything went wrong. The result was a verified speed record, an experiment that turned a stretch of Colorado track into a rolling laboratory, proving that rail could serve as a test bed for propulsion breakthroughs under extreme conditions. Every odd-looking rail machine rolling today is a direct answer to relentless, unseen pressures, physics, fatigue, security, survival. As networks stretch to meet global demand, these engineered outliers quietly decide what moves, what launches, and what endures. The future isn't smooth. It's shaped by the strange. Subscribe for more stories beneath the surface.